Hello, Professor Bloom. This is Team ToDo with Mikkel, CG, Harold, and myself. So our code is implemented based on tree structures with subtrees under each node. So each node contains an element in the array which has been sorted. So for malloc, using the tree structure, when we call sbreak, we release a tree node which comprises of a pointer to the next tree, an element in the array, and address to the previous node. So our tree is what allocates the memory to make the program dynamic.
Harold here. So I'm going to be talking about the free function. So our free function uses a tree structure as well. So basically we negated the tree composition, which enabled us to remove the current node that we'll be working on. Meaning the removal of that current node is going to serve as a way by which we're going to deallocate the memory from our program.
Hi, Dr. Bloom. This is Group To Do with Mikkel, CG, OZ, and Errol. I'm basically just gonna walk through the code we have and just try to explain everything we did. And okay, we started by initializing all our test values. Like we have two registers which we're going to test. We created a loop, and then every time we increase the loop, we increase the number of instructions that we're going to test, and then every time we increase the loop, we go through malloc, we allocate more space for that, and then to test our performance. So if we in our T register T1 and T2 are the two registers holding those test cases. So we initialize T1 to 0 and we initialize T2 to 0 too. But we gave T2 a certain value. We could give it 5 or 10 depending on what we want, how many times we want the loop to go So that is basically how we tested our malloc, allocating our space. But before we did that, let me just walk through the code and say what we did specifically. We implemented a tree sort, and then in the tree sort we have like a left node, a right node, and from the left node and the right node, which we initialize because at the beginning we have nothing. From the left node and right node, we jumped to a create node where we have to create the node for it. And when we create a node, we have to insert a value into it, and that is why we use that. That's why we use the syscall liv05, and then we syscall it. So this will prompt a user to input a value, and every time we input a value, we now go to another part of our code, which is the insert in root. And every time we go into insert in root, it insert the inputted value into the root of the node we created from the create node, from the jump and link to create node. So when we create a node and we insert a value into it, we basically allocate some space, so that if we allocate some space for the three the left, the right node, and the value we're putting on each node. That would be 12. That would be 12 bytes, and that is what our malloc. That's what our malloc is. That is what we have for our malloc. Our malloc basically allocates 12 bytes of dynamic memory for those three, the left, the right, and the value at each node. Our code also have a part where we need to test if we have enough memory because we can allocate memory, but we don't have enough memory for that. So in that case, we have a branch equals 0 to test if we have enough memory. If we have enough memory, we'll go through the code and then we'll implement the stack, and then what we inputted, we're gonna insert it on the node. But if we don't have enough memory, our code prints out our code is supposed to print out sorry, not enough memory. So what we essentially did is we implement we use the S break to dynamically allocate memory for our nodes and the value at each root of the node, and then we use the stock to create a node and to insert value in the root. And I hope I went through everything. I think I did. And I think I need to talk about some of the challenges we had during when we were executing the code. First, we had some issues with our code, which we presented to you, and you told us that it wasn't the right way to do it, so we had to redo it again. And first, the most important, like the biggest problem we had was just understanding the project and implementing it like you wanted us to. So we hope this code is um, at least what you wanted. And thank you so much. Have a good one. Bye.
So Harold here. So I'm going to be talking about how we tested for performance. So basically there's this formula, execution time, which is equals to instruction count times the CPI divided by the clock frequency. So given the number of the instructions that were given, we're able to calculate our performance by counting the number of instructions. So for store words, we had 13 instructions. Load word, we had 10. Branch, we had 3. And then other instructions, we had 23. So basically, the CPU time for store word was the 13 instruction times 2 cycles divided by 2.5 gigahertz, which is my computer's clock frequency. And I got 10 seconds for that one. And for load word, we had 16 seconds. Branch, 2.4 seconds. And other instructions, we had 27.6 seconds for the CPU time. And so this is a graph that illustrates the instruction count and then the CPU time.